Today's webinar is on grid infrastructure. Sorry. The National Association of Regulatory Utility Commissioners offers a monthly innovation webinar for all of its members and stakeholders. This is sponsored by the U.S. Department of Energy and hosted by the Center for Partnerships and Innovation, which is the NARUC Technical Assistance Team. The next webinar in our series will be on advances in resource adequacy on March 16th. And in the interim, we look forward to seeing you at the NARUC Winter Policy Summit, February 12th to the 15th in Washington, D.C. As I mentioned, today's webinar is on grid architecture, why it matters. And we are pleased to be joined today by an esteemed panel moderated by Commissioner Catherine Paratick from the Michigan Public Service Commission. While Commissioner Paratick introduces herself, we'll get today's slides up.
Thanks, Danielle. Appreciate it. And I'm excited to be here and a part of this webinar series. This has been a really valuable series of conversations. As Danielle mentioned, I'm Catherine Paratick. I'm a commissioner on the Michigan Public Service Commission. Been on this commission for 2 years now. And but prior to joining the commission, I have a background in energy storage project development. I spent about a decade either developing the technology or developing the energy storage projects. So really big batteries for the electric grid in the form of lithium-ion batteries, flywheels, compressed air energy storage, among other fun technologies. But now, in my role as commissioner, I think a lot about the state of our grid here in Michigan. We are a state that has fully deployed AMI, advanced metering infrastructure, for years now. We were pretty early on that curve. And we're seeing an uptake of ADMS to a lesser extent, some DERMS technologies too. We're also a state that's heavily impacted by summer storms that cause really extensive outages. And 2 of our major utilities in the state of Michigan both have net zero climate goals in the near future, one in 2035 and one in 2040. So that all combined with seeing a significant change to the electric grid, a significant uptake of electric vehicles and the associated infrastructure, additional electrification of appliances. You know, there's a lot of change that's happening in our state. And we also have a pretty large state with some dense urban areas with very old decaying infrastructure, and large portions of our state are pretty rural, especially our Upper Peninsula is particularly remote and spread out and poses some pretty different challenges. But it's my job as a commissioner to ensure that all Michiganders have safe, reliable, accessible electric services at reasonable rates. And I want to ensure that we're thinking actively about how to structure the future electric system to ensure that we're making effective and sustainable and equitable decisions that will be long lasting and that will enable rather than hinder new technologies that will increase resilience and reliability, and that will provide a framework for the modernization of our electric grid in the changing world. So this is a lot to ask out of a webinar, but luckily there are 3 experts here to help me tell me how to do all of this over the course of the next hour, who I will introduce in a moment. But first, I'll just outline the plan for the presentation today. First, we're going to go through presentations from each of the 3 experts that we have with us on grid architecture with a Q&A session at the end. We'll save some time for that. This is a Zoom webinar format, so you'll need to use the Q&A function to be able to ask the questions during that Q&A section. And then I will read out out loud your questions to the presenters during that time. We're going to save all of the substantial questions to the end of the presentation, but if you have any clarifying questions that would benefit to be asked in between presenters, please do type those into the Q&A function and I'll be sure to ask them during the transitions. So if you, thank you. On this next slide, these are our introductions. So these are the panelists that we have with us today. Kicking us off will be Mark Patterson with Stratagen. We owe him a big thank you. He's joining us from Australia in the middle of the night right now. A globally connected energy system transformation leader with 25 years of experience in technology strategy, power systems architecture, and thermal and fluid systems. He's known for his expertise in leading the navigation of complex issues, systems thinking, and co-design of transformation pathways. Then we'll have Lorenzo Christoph, a principal market architect, as an independent consultant, focusing on power system transition to integrate high levels of DERs. His expertise includes wholesale power market design, DER participation in wholesale markets, distribution system operator models, and distribution level markets, microgrids, energy resilience, whole system grid architecture. And then finally, we have Kay Aiken, who is the Chief Product Officer of Dynamic Grid, a utility software company based in Portland, Maine. She's a graduate of Pennsylvania State University with a degree in energy sustainability engineering. Me too, Kay, not from Pennsylvania State, but from University of Michigan. Kay she's a recognized transactive energy expert, as well as distributed intelligence in the electrical grid. She's on the board of GridWise Architecture Council and working on architecture and interoperability in grid modernization and smart grid. So we have a lot of experts with us today. And with that, I'm going to pass it over to our first presenter, Mark.
Great, thank you, Commissioner. All right, so and good to connect with you all from Australia, and to be speaking with my colleagues Lorenzo and Kay as well. So I will be speaking on the topic of really getting into the why around this topic of grid architecture, with a focus on taming runaway complexity, cost, and unintended consequences. And the reason why that's absolutely critical is that it's really important to acknowledge that the grid as we know it has served us so well is actually an ultra large scale complex system. In fact, probably one of the most complex cyber-physical transactional systems ever created by humans. And now these systems are going through a once in a century scale of change, really unseen since Edison and the original Tesla. And so in one sense, I'm speaking to you from the future because it's Friday here. It is a little civilized. It's 6:30 something in the morning, so it's a little better. But in Australia, we are actually experiencing one of the world's fastest grid transformations as well. And so that kind of provides some context to what I'll be sharing. I want to just finally acknowledge too CSIRO, our National Science Agency, and AEMO, the Australian Energy Market Operator, who have supported the work that we've been doing on grid architecture. Next slide, please. So we've mentioned the speakers, and so obviously the heart of this grid transformation is that we're moving from highly centralized generation and essentially passive loads to a future that's increasingly hybridized, if you like, by the combination of centralized and distributed generation resources, and also vastly more active participatory loads and flexibility. And so you're seeing this very, really a monumental transformation from a very linear, unidirectional bulk power delivery system to a much more dynamic, interdependent system. Next slide. And in this context, the grid is becoming, even if it was possible, as it were, vastly more dynamic and systemically complex. This is a context where, regardless of all of the changes that are happening, as one of the introductory slides said, even transitioning from hundreds to tens of millions, indeed hundreds of millions of participating resources located on both sides of the supply-demand, if you like, bifurcation, customer demand and variable generation must still be kept in balance every microsecond of the year, even as the proportion of dispatchable generation declines. In Australia, we're seeing quite a accelerated withdrawal of conventional generation, which is bringing this really to the fore. Next slide, thanks. Actually, there might be some other, okay, so just on that text, before we move on, sorry, there was just some text that should have come up there. If you could just go back one click. Apologies. So the point here was that, and very importantly, similar to the modernizing aerospace sector over the last 2 decades, I think the power sector globally is facing a situation where we need additional tools to tame the runaway complexity, cost, and potential unintended consequences of making specific changes to this ultra complex system. The aerospace sector has found that you really can't just change any number of incremental adjustments without actually having a significant impact on the systemic whole. And one of the dangers of not having a systemic approach to this kind of scale of transformation is the creation of the propagation of a whole range of unintended consequences, creating additional complexity as a result of making those changes. So really what we're talking about here is a systemic approach to how we collectively navigate this monumental scale of change. Thanks, next slide. So there's often, a lot of questions about, well, why do we need this? We don't seem to have needed it for the last 10, 20, 30 years. What's the basis for why a systems architecture-based methodology is so critical? And I would assert that it's absolutely fundamentally important to the management, the transition of any ultra complex system. The first 2 points are that every complex system ever created by humans has an underpinning structure or architecture that is fundamentally important to its operation. And I think the tricky part about architecture is that it's less visible. It's less visible than system components. So by system components, we're talking about the energy storage, the poles and wires, the generation plants. It's also the components in the sense of rate design initiatives, regulatory changes. They're essentially systemic components that are more visible, tangible, and so on. But as the first point says there, every complex system has an underpinning architecture which has disproportionate and irreducible influence on what that system as a whole can cost efficiently and reliably perform. So what is that architecture? How do we actually understand what that is? If you could just click once more, essentially the established systems architecture discipline, which really is the basis, a core part of the underpinnings of grid architecture. It's an established discipline that provides the formal tools for examining the elements and actors of the complex system or the components, the critical linkages and relationships between them, and the emergent behaviors of the system that arise as the system changes over time. So just a point to note here is that the Commissioner noted the impact of summer storms and so on, and emergencies that arise, if you like, in the context of these complex systems. Emergent behaviors are the positive desired outcomes of a system. Emergency is also a systems word in the sense that when you have systemic failure, when you have a system that hasn't actually kept pace with the structure, hasn't kept pace with what the system is being expected to do, for example, decarbonize in ways that we've never had to before, emergencies are what can actually manifest from the system itself as we failure to deal with those systemic underpinnings. Next slide. So I think this is a really key point, and that is that one of the things that's happening in decarbonising power systems, regardless of the proportionality of DERs or centralised renewables and so on, regardless of the differences across different scenarios and different jurisdictions, the nature of the transformation is that the traditional historic supply side, demand side bifurcation is essentially eroding. It's in terms of its strict bifurcation, where there was a location where all the generation, or an end of the system where all of the generation was hosted. The other extremity of the system was where all of the customers and loads were essentially located, and you had a unidirectional flow of electrons. A decarbonising system requires fundamentally more and new sources of flexibility, particularly as you have the proportion of dispatchable synchronous machines declining in proportion to the growth of both utility, VRE, and also DERs. And so efficient operation of a decarbonising system of whatever type requires an entirely new level of whole system interdependence. That's a really key point. Just one click if you could, please. And so just to summarize that, 21st century grids, and this I think is a global realization, 21st century grids require bulk energy, transmission, and distribution systems together with deep demand side flexibility to be capable of functioning holistically in a manner that is critical to avoid overbuilding, duplication, and stranding of investments. This is a really critical point in terms of, and just bear in mind, there's the system balancing dimension to this, which means that there needs to be a capability for this system to be able to balance supply and demand instantaneously every millisecond of every year. And so that is the context in which we're talking about what's on this slide. Next slide. Thanks. And I think this is the last slide for me, but I think a really important point here is that the question of how in the world do we navigate these kind of scale of transformation, which none of us in our careers have ever faced anything so monumentally large and complex. So that's just the reality. We're all still humans. We're all struggling with how do we navigate this. Grid architecture tools empower stakeholders to better evaluate grid expansion proposals by applying not only a present forward, in other words, we stand in the present and we increment our way forward and we hope that we're kind of making the right decisions for the future, but also with a more future back thinking and analysis. In other words, the systemic tools give you the capability to, for diverse stakeholders to start working on and understanding, well, what are the plausible ways that the future is going to need to manifest, or at least the options, the scenarios, the systemic changes that within certain boundaries are going to be really containing what that emerging future is going to look like. That's not going to be one future singular, there's going to be futures, plural, but it gives you a whole bunch of new capabilities to change the nature of the discussion with diverse stakeholders, with ratepayers, with commissions, with governments on the nature of how we actually think, not just from the present forward, but also with a more future resilient, future ready set of lenses. Just one further click, if you wouldn't mind. And, you know, just the example there is to say, well, as you're working with stakeholders, how might our portfolio of multi-billion-dollar projects be moderated for a future where whole system coordination, what we were just talking about, can significantly enhance operational efficiencies? And just to give you a couple of data points on that, ultimately, a number of international studies that have been undertaken in Australia, in the EU, in the UK, and in the US, in terms of order of magnitude, or identifying that the kind of whole system coordination, whole system optimization potentially unlocks in the order of about 10 to 15% of annual TOTEX, in other words, CapEx and OpEx. So just to give you an order of magnitude sense of the money on the table here. And I think at that point, I hand to my colleague, Kay Aiken, if you could just go to the next slide. Thanks, Kay.
Okay, you're muted. Please unmute yourself.
Okay, I'm sorry. Thank you, Mark. You are always very hard to follow, but you laid a great framework for background on why it matters. I'm going to talk about the technology transitions and networks of the system and how we kind of look at the architecture or structure of the grid and determine what our future requirements are going to be. Next slide. So technology transitions where we're looking at this complex system are not easy. And the point behind grid architecture is to try to make sense of what those are. And one of the interesting things about managing these complex systems and these massive transitions, I mean, we're looking to go from maybe 10% renewables to 100% renewables in the next 30 years. And it's not going to be a smooth ride. And as Mark said, we're looking at both present looking to the future and from the future coming back to the present. And there's going to be these curves where at some point we're going to not going to be able to progress and actually have to make a step change to another spot in order to continue. So this transition actually requires parallel implementation paths, and grid architecture can provide those paths for these whole system approaches to looking at the system. Because in order to get to the energy transition, we have to evolve together things like storage and generation and the distribution and transmission systems and grid edge technologies and controls, and regulation actually drives those things in many, many ways, because how you manage the markets versus how you manage rate design and how you manage value transfer in the system actually have a great effect on how that system transitions. So those are the kind of things that we have to step back actually and look at in a whole system approach to manage this massive transition change. Next slide. And another thing that we have to understand, and that's kind of related to the idea of where we're looking at storage and generation and distribution and transmission, is we actually have a network of structures. And that's one of the things about grid architecture is it's an analysis and understanding of the network. So there's not just the infrastructure, and infrastructure is structure. You know, how do we run our wires from the transmission through the sub-transmission system down to the distribution system? But there's also structures within the markets. There's structures within digital controls and the digitization of the system. There's sector coupling, which is the idea of some point the transportation system, and we're getting there with EVs, is the transportation system and how the transportation system is actually dynamic and actually affects how the electrical system needs to provide services to transportation. And then, of course, all of this which is where NARUC comes into play, and where all of you are so critical to this transition, is regulatory structure. How do we regulate this system to the benefit of what is ultimately the consumer and the public? And that is the thing we have to keep in mind from the beginning. And overall, of all of these things, is how do we manage that structures using regulatory structure? And this is where grid architecture is not just architecture in the sense of like a building architect, where you have, I'm building a building. We're actually looking at systems architecture. And it's really, really critical for taming this complexity, as Mark says, taming grid complexity and navigating this network of structures and systems, so that we can provide broad or operational coordination. As Mark said, there's a lot of money on the table for efficiencies if we do this right. Next slide. So to talk a little bit about operational coordination, we require the interaction between markets and control structures. And, the economists will say, if we just get the market right, everything will be fine. And the control engineers say, if we get, and I'm a control engineer, if we get the algorithms right, and interoperability, everything will work fine. But actually, no, it's actually a merging of these two things, where market systems and control features actually come together and mutually support each other, all the way from long-term planning and investment. I'm starting to get an echo back for some reason. Long-term planning and investment through system optimization on hourly, daily timeframes, and then system operations, which the utilities are dealing with all the time, is how do we handle what Mark had said is about flexible loads? How do we on minutes and seconds be able to control those? Those are all actually regulated by how we regulate the systems and how we do value transfer within the system. So this is a really, really important part of to remember, is how do we use regulation and being able to understand how that regulation can affects the overall system through the process of understanding grid architecture. And grid architecture, again, being not just the structure of the system, but actually how the system works together and interacts with each other. Next slide. So to reiterate, which is really the point of this webinar, is grid architecture is critical for making these key structural choices, so we can enable a more intelligent and self-optimizing power system to get to decarbonization in 2030, 2035, 2050, depending upon what area you're in. And it's really about good for all. We want to have system benefits and societal environmental benefits from decarbonization, as well as support the customer with benefits for them. So it's this Venn diagram of good for all, and all of these things have to come together, the affordability and provide new offerings and new market structures, and all that can enhance decarbonization and help with equity so that no one's left behind, and also make the system cheaper, lower the amount of infrastructure we have to build, the lower the operational costs to make things more efficient. And then the engineering part of it is, how do we manage these things? So next slide. So there's going to be a whole pile of new future requirements of this, what this future is. And there's this, we'd like to look at the metaphor of the bridge to the future, is grid architecture can actually help us understanding what these new emerging requirements are, so that as regulator, you can understand and adapt over time through these step changes and these parallel processes to adapt and evolve the grid. And those are what the previous slide was: affordability and equity, and how do you manage variable generation, and how do we do dynamic load balancing? How do we make loads respond to the generation, what is going to be variable, solar and wind? We now have to have not just a system that was centralized before, and you would ramp up generation to meet load. Now the load actually has to start following the generation. So all of these things, grid architecture helps to understand, clarify, and come up with practices and processes to make this more efficient system. Next slide. And so the future questions for regulators for managing this future is, what's the solar adoption going to rate be? Are you going to have only one house in a neighborhood take solar, or are you going to have 100? The solutions for how we manage that transition are going to depend upon the answers and questions, and what questions and answers we have on that stuff. What's going to be the impact of federal incentives here in the U.S.? We had what is really fundamental change in federal incentives with the IRA and the building infrastructure, the bipartisan infrastructure law, or IIJA. What's going to be the impact of FERC 22 and what kind of tariffs? I mean, there's estimates, and we've talked a lot about the amount of money we need to spend on generation, or sometimes we've talked about how much storage we have to have, and then transmission. But we also have the distribution grid, and there's some estimates of the distribution grid upgrades being in the order of $2 to $10 trillion, because we have such old infrastructure, and we have to find ways how to increase the utilization of that infrastructure so that we can keep rates affordable for all. So those are the kind of things that we have to talk to. And I'm gonna leave with one last thought before I hand it off to Lorenzo. Is, if utility comes to you and says that customer X can't connect because we don't have enough capacity, or we don't have the controls to manage it, or whatever, what do you have to say? And I think that's really the big question for regulators, is how do we answer those things? Because I know in my jurisdiction where I live, 70% of the substations can't handle DER. And how do we manage that and tell customers, sorry, we can't serve you? So those are the kind of questions that the grid architecture practice can help mitigate and help balance concerns across the entire system. And I will hand it off to Lorenzo.
And Lorenzo is joining by phone. So we have the slides up on the screen here. And then Lorenzo, if you could just unmute on your phone, we should be able to hear you. We cannot hear you quite yet. Give Lorenzo another couple seconds to try to unmute over the phone. I see you dialed in, Lorenzo.
If it's helpful, if Lorenzo doesn't make it, I can probably just step us through that content that actually Lorenzo and I have presented previously, but happy to do that if he's not able to join.
Thanks, Mark. Yeah, we might do that. Let's give him just another 30 seconds or so to attempt. I know that there's some behind the scenes efforts happening right now to try to unmute him. So we'll
That
give it
sounds
just
good.
30 more seconds, and then we'll kick it over to you to take Lorenzo's section.
I appreciate it, Mark, because I could not give his slides.
Well, I'm not going to compete with Lorenzo, but you know, it'll be a second best.
All right, Mark, why don't you get started? He's working on it. And Lorenzo, if you are able to eventually unmute yourself, I'm sure Mark will not mind if you interrupt and take over.
Yeah, no, that's great.
Sorry,
right, well,
I'm just sorry, Mark, just one more thing. Lorenzo, if you can press *6 on your phone, I think that should unmute you. But Mark, why don't you get it kicked off?
Sure thing. All right, so I know Lorenzo was really keen to just get into some of the detail around, okay, how do we go about this? And you know, as Lorenzo would do, just starting with kind of the two uses of the word architecture. So architecture of a complex system is the arrangement of the actors who comprise the system, along with their responsibilities, functions, roles, and interactions with one another. In terms of grid architecture, which in Australia we refer to as power systems architecture, is a discipline and set of methods for representing, analyzing, and understanding the electric system as a whole system and tracing the impacts of changes to the system. And I think what he's getting at there is, in a sense, as Dr. Jeff Taft, a colleague of ours, formerly of PNNL, would often highlight, that the power system, the grid, is a very complex tapestry, and you pull on one thread and the tapestry will bunch up somewhere else. And so, and this is exactly the reason why the aerospace sector uses these kind of capabilities, because they understand the implications that aircraft, where you've actually got systems fighting each other, or unintended consequences propagated through a system when you make a change over here, will actually have big impacts on the function of the system holistically. Next slide, thanks. Okay, actually, I might just back one, sorry. There was just some text that came up there. I'm sorry. Whoops, here we go. All right, thank you. So in the regulatory process, the discipline and the methods of grid architecture assist regulators to better align the performance of regulated entities with the public interest. And I think that's a really important point, is that while grid architecture can sound like almost a geeky kind of abstract kind of set of disciplines that are impenetrable, in reality, what we find is that as we work with stakeholders, that there's a sort of a process of, look, this seems impenetrable, really complex. But as people start to get a handle on it, they start to say, wow, this is really helping us understand the power system in ways we never did. We've never, in the last decades of our careers, we've never had to think about the power system in this whole system, way to really understand what's under the hood of those 7 structures that Kay referred to in the network of structures. That really helps both technical and non-technical stakeholders to start having a different quality of discussion about what it's going to take, what are the trade-offs, what indeed is the public interest, how do different stakeholders, how do we balance the diversity of trade-off decisions that need to be made as we think about the regulatory process. Next slide, thanks. And Lorenzo, if you can, feel free to jump right on in anytime if you can make it. But this is, Lorenzo was keen to just step through some of the sort of key steps in the process, because it's not just abstractions, it's a very tangible, stepwise process. And so, firstly, it's ultimately about thinking about the structural phase, or the structural phase is really about making decisions about the system and the market structure. And we'll get into that on the next slide. If you could just click, I think some of this is going to come up automatically. All right, so there's sort of a broader decision process that we'll talk about around, holistically system and market considerations. That leads into design and implementation phase, where focusing in on policy and technical details to implement the adopted system and market structure. Just perhaps if you could just bring the content up, and then I'll speak to it all. Okay, and so there's a monitoring and feedback phase to evaluate system and market performance and guide adjustments as needed. So this is kind of like a meta kind of view of the process, where you're thinking holistically about the system as a whole. And what we're talking about there is T to D to C. In other words, transmission and bulk power system, distribution systems, customer systems, how all of this, how do we need to think about this much more holistically? I think we just lost the slides too. Secondly, how does that lead us then to actually have a different quality of discussion with regard to the detailed design of the grid? And I think, just while we're getting the slides back up, I think it really goes to the topic that one of the best kept secrets of systems architecture and systems thinking is that any number of changes to individual components, any number of individual initiatives will never actually be capable of compensating for an underpinning structure that's no longer fit for purpose. And so this detailed design phase, where you're actually looking at the details of the policy and technical considerations and the cyber physical dimensions, if we're kind of just dealing with that from the present forward, incremental changes, and we're not thinking holistically, and we're not thinking about what are the structural underpinnings, that's going to cost an awful lot more. It's going to be more brittle. It's going to be less scalable. And overall, it's going to actually lead to rework, unintended consequences, and so on. Might be good if we could just go to the next slide. We'll bring up any remaining content on this one. Okay, so design and implementation follow structure. Monitoring is ongoing because the electricity system is actually a complex adaptive living system. Might be another bullet that's about to come up there. And most adjustments are within the existing structure, design and implementation. So I think that's an important point, is that architecture is one of these things that, because we haven't had to do a lot of thinking about it, it can be a bit like the fish takes the water for granted, that we frame so much of our thinking, even unconsciously, around, for example, the dominant paradigm of the last century, which is a very strict supply side, demand side bifurcation, and quite a structured, fixed view of different roles and responsibilities. This actually helps us not to just, change all that for the sake of changing it, but to actually gives us the intellectual tools to actually start thinking differently about, well, what are the options here for the changes we need to make? How might we do that in a way that provisions the entire system most cost efficiently to make the kind of decarbonisation transition that we need to make? Next slide, thanks.
Hey, hello everyone. This is Lorenzo. Can you hear me?
This is much better. Thanks, Lorenzo. Over to you.
Hey, okay. Thanks, Mark, for filling in, and sorry for the mishaps. Technology was working against me, at least for a while this morning. I'm only on phone, so I can't really see the slides, but I believe that we've just advanced to the slide that has the heading Grid Architecture, the Structure Phase A. Is that what everyone is seeing?
That's correct.
Okay. So there's a number of animations through that slide. I think for the sake of time, go until you've got 4 blue boxes across the top and then an orange box on the right. And then that's the full slide. And then I'll quickly talk through that. So Step one, this is really the logic of the structure phase, which was the first box on the previous diagram. Step one is to define what the public interest is. What are the goals we're trying to accomplish? What are the goals that we expect, especially the electricity system, to support? And that can be policies, policy mandates, various societal interests. Step two then says, well, let's get specific about the performance of the system. What does it need to do? When we think about that from an outside the system perspective, in other words, as the power system interacts with society, what are the impacts of its behavior? How does it perform? What qualities do we want it to have? And that gets to things that are familiar, like affordability and reliability and ease of interconnection, say, those sorts of things. Then when we get to step three, now it's looking inside the system and saying, well, to get to the performance that we need, what specific functions need to be performed? How does the system need to operate from an internal level? And that has to do with things like connecting resources, being able to dispatch them, to balance load in real time. There's a whole host of operational things that you all know about. But the point is that there's going to be a question coming up next, which is about which actors are responsible for what things. And the logic of grid architecture says in step three, let's identify all the functions first, the roles, responsibilities, what needs to happen for the system to work, and then think about who's going to be responsible for what. So when you get into step four, then we can look at different architectural or structural models, and that is, how do we want to assign all of these functional requirements to different actors? How do we want to specify their responsibilities and their interactions? What things do we want to say about market structure? For example, which functions are best served by a regulated monopoly? Which functions are best served through competition? And as we see with the growth of distributed resources, there are lots of new competitors emerging on the scene. So we think there about, well, which functions need to be unbundled so that they can be separated in a market context. Finally, then structure phase A ends up with policy decisions that are going to really affect the system structure. So one more slide and then we'll be done. I have a short list of takeaways. And there's 5 bullets on this, so if you want, put them all up at once. The first takeaway, the structure phase, what I've called A, is where the system and market structure policy decisions are made with the idea of best aligning system performance with the public interest. Now, what may not be obvious, but I think Mark mentioned this earlier as well, that the electricity system has an existing operating and market structure to it. It's not like there never was a structure. There is one. And there's the status quo structure and how it works today, which has largely evolved over the last 100 years. So the grid architecture as a discipline starts by mapping and understanding the existing structures. That's always the starting place, because from there, we want to consider the impact of potential changes. Now, reiterating a bullet on an earlier slide, if there's major changes in the conditions surrounding what the societal goals are, or other aspects of the industry, the major changes that Mark and Kay talked about, then that really warrants revisiting structure, because all of the structures that we have today evolved under a certain set of objectives and industry conditions and really social conditions and political conditions. Final bullet, a decision not to revisit the structure. That is, let's skip A and let's go right to design and implementation decisions. Let's think about, grid modernization types of enhancements and so on. If you start moving into phase B, the design and implementation, and you don't give reconsideration to phase A, the structure, then essentially you're making an implicit decision to retain the status quo structure. And that might be the right decision, but often it's overlooked and not dealt with explicitly. So that's where I want to end. And thanks all for your patience with our mishaps, but glad I finally made the end of it. So we can skip. Well, the last slide just has a funny picture on it, but I'll just hand it back to the commissioner, and we can get into what's next.
Fantastic. Thanks, Lorenzo, and thanks, Mark and Kay, for the great presentations. Thanks everybody else for putting up with our technical difficulties today. But I think we got through a lot of content in the 51 minutes that we've been talking about this. So we have about 8 or 9 minutes left, and there are a few questions in the chat that I want to ask, and a few more that have been sent to me directly. But first, I want to start with a question that came to me as you all were going through this. So I want to talk about how this helps us as regulators, and if there are any other regulators or staff or utilities on the call who are looking to address costs considering these new investments. So how can we as regulators use this grid architecture to identify the pace and timing of the new investments to minimize bill impacts without a negative impact on grid reliability? And I can kick that to anybody who wants to take that first.
Well, this is Lorenzo. I'll jump in with my own perspective on this. I think over the last 100 years, we've evolved a system that relies heavily on monopoly structures. And what we saw in the 1990s with the creation of wholesale power markets, that it required unbundling some of those monopoly structures and enabling competition. And so as we think about massive investments in the future grid, I think looking back at where are the opportunities for competition can be really important. Because if we're making investments entirely under the monopoly structure, then all the risks associated with that investment are placed onto ratepayers. And risks with new technologies have to do with things like obsolescence. How long will this investment be good before something much better comes along? Or performance, where we're using unknown or new technologies. What are the risks that it won't perform as intended? And so a competitive market where you have now private investors responding to RFPs and offering products and taking responsibility for performance may be a good way to pursue savings for ratepayers.
Thanks, Lorenzo. And just to add to that, I think that one of the major concerns around this topic is, what is our theory of change? And I think that's not just an academic or abstract question. It's when you face the kind of scale of change and pace of change that we're now all facing to this ultra large scale complex system, you have to actually act rationally. You have to ask the question, what is the nature of this? What set of tools, what kind of ways of thinking are going to be sufficient or commensurate? Is it sufficient to do what we've done in more stable times, and that is break things down in a very reductionistic way into specific issue in isolation type problem solving? And so we make an investment here, or we make a change there to a regulatory mechanism. Those things are fine in more stable, slow-moving times. Where you have wholesale transformational change, where in 2050 our power systems will need to be radically different from what they are today. That forces us, if we're rational, to actually ask the question of, how do we bring some lenses here to really identify what are going to be the mission critical investments? Are those investments scalable to the plausible futures that are plausible? Are they extensible? Are they, to use a word, future-proof? I don't particularly like that word because it says too much. I think of future resilient decision-making. In other words, how do we build the toolkit as regulators, as stakeholders, as customer advocates, for really thinking in much more robust ways that other sectors are currently doing and that our sector has not really been doing to this point, of scenario-based, future resilient options and trade-offs. I think that's at the very core of how we navigate this, what is going to be the next decade of fundamental transformation. I think that's what we're tooling up for. we need to tool up for not just the next year or two. It's about how do we tool up for the next decade of monumental transformation.
And I'll build off that slightly little differently. It's about breaking down the silos between these things, there's no silver bullet. There's no one answer to things. And I do a lot of optimization, large scale optimizations, and it's a balance between lots of different things. So it's going to be how much you invest in transmission, where you invest in transmission, how much you invest in the distribution system, and that is a moving target. And that was kind of one of my slides where we talk about these transition paths where at some point you've maximized one particular lever that you have, and you actually have to move to a different lever. So that's really, you have to be flexible as a regulator to understand at what point, and that's what grid architecture does, is allow you to explore and understand where that dichotomy point is, where you've got to use a different lever to get the result, which is ultimately lowest rates, most effective, most efficient electrical grid system.
Thanks for that. I want to go to one of the audience questions. This is from Alan. He says, in Europe, we're going one step further by thinking of an integrated energy system, combining all networks and storage across electricity, gas, and heating and cooling energy carriers. Would that make sense for the next generation net zero energy system in the US, maybe in some regions like the Northeast at least? Are there any opinions on that?
Well, I think that's a really good point. I think I tried to make that point is, as we electrify our transportation system, our transportation is going to be very tightly coupled to our electrical system. So I think that's the concept is, and that's again where architecture comes into play, is understanding what those interdependencies are between those. Where do you put DC rapid chargers? There's certain places where you can, there's certain places you can't. So you have to understand the transportation patterns in order to inform how you build the patterns of the structure of the grid from an engineering standpoint, and how you balance rate tariff regulation, et cetera, to make that not a burden on the infrastructure, but actually an advantage to the infrastructure.
Yeah, I was just simply quickly add that one of the nodes that Kay was addressing in the network of structures is sector coupling. And so that's exactly to the point Alan is making, that grid architecture is very alive to and very engaged with the fact that one of the 7 overlaid structures, if you like, is how the power system interfaces with an increasing range of water, gas, hydrogen, transport, a whole range of different systems as part of the new sources of flexibility that are critical for a decarbonizing grid.
Okay, well, thank you very much. We have reached the end of our hour. I feel like we could keep talking about this for so much longer. There are still some questions that we didn't get to answer in the chat. A lot of great engagement from the audience. Thank you all for attending. And thanks so much to our panelists, Mark, Kay, and Lorenzo for sharing your expertise on this super important topic of grid architecture. And with that, Danielle, any last word?
This will conclude today's webinar, but we will be posting the recording and the PowerPoint presentations on the NARUC website. You can find the link in the Q&A before you go. Thank you all so much.
Can I say one thing? I think all 3 of us will also be available if anybody wants to engage us with more information,
Yeah.
That's great. Thank you all.
Thank you.